My name is Dr. Umish Srivastava. I'm your session chair, and I am working as Executive Director at Indian Oil R&D Center at Faridabad. Uh, Welcome all to this session on innovations in bio and synthetic fuels. I'm sure you all are well aware that the synthetic fuels which are on the radar today are majorly ethanol, methanol, and the hottest synthetic fuel that I personally consider is the green hydrogen. So that's something which is being discussed and talked out, and actually is most of us are hoping our uh, best endeavors to ensure that this synthetic fuel comes out to be true. And with respect to the biofuels, I understand there are many which can be derived from biosource. And my personal bet would be biogas, which is now in Indian context being discussed as a compressed biogas (CBG), and the Satat program that has taken off very well in the country. To know more about this and what all are the innovations happening in this area, we have an array of speakers. I'll request my partner here, Dr. Banerjee, to take the session forward.
Good morning, everyone. Thanks to Dr. Srivastava. My name is Soumendra Banerjee. I work with Honeywell UOP and I've been there for about 23 years now, working in the area of sustainability. So, since we have 5 speakers, without any delay, may I call upon the first speaker, Prasanna Kannan, to present on using synthetic fuel to decarbonize the transport sector worldwide.
Morning everyone. Prasanna here. I'm a commercial director at a company called Petroleum. We're based in the United Kingdom, and I'm going to talk about synthetic fuels that we make, which are actually replicas of synthetic, fossil fuels. So we make synthetic hydrocarbon, which is sort of the next step, we believe, after green hydrogen. Our tagline is simple. It's fuel reinvented. So we believe in liquid fuels, and we'll come on to some of the reasons why. We think liquid fuels are here to stay, primarily due to energy and density and the infrastructure we have around us. But we believe the problem is not to do with the engines or the infrastructure, it's to do with the fuel itself. And so what we're trying to do is to move from a linear fossil fuel paradigm where you dig out carbon that's been stored in the earth for millions and hundreds of millions of years to a synthetic circular paradigm where you actually create fuel using carbon from the atmosphere and green hydrogen. And that way we have a sustainable liquid fuel paradigm. And so that's what we're all about. And in the future, for now, we're aiming to create replicas of fossil fuels. But in the longer run, we are, have the potential to make superior fuels to what we have currently today. So to just spend a few slides talking about our company and our history. So we were founded in 2020 by Paddy Lowe. So I don't know if there's any Formula One fans here in the audience, but Paddy is a very well-known man in Formula One. So he's the most successful technical director in Formula One history. Headed up Mercedes during Lewis Hamilton's successful time there. But another co-founder is Professor Nilesh Shah, who was the head of chemical engineering at Imperial College and is a leader in sustainable fuels in his own right. And as I said, what we do is we create carbon neutral synthetic fuel. And when we say synthetic fuel, we mean hydrocarbons. So we create replicas of fossil fuels. As I said, this is a few steps behind the other fuels that you probably hear about today, which are a bit more advanced and progressed. Our technology is a bit earlier stage. But in 2021, we got the Guinness World Record for the first ever flight done using synthetic fuel. And one of the great things about our fuel is we have 100% drop-in capability. So we can make all fuel types, and it's 100% drop-in. So for example, in that Guinness World Record flight, because it's done under Guinness conditions, is very strict. They empty the tank of the plane, and we then put in our fuel straight from our reactor and flew the plane. And so we're already able to achieve the complex molecules, so the RON levels for gasoline, the aromatics for jet fuel, and it's something that kind of distinguishes us from competitors in the space. And ultimately, it comes down to a proprietary process we have called Direct FT, which stands for Direct Fischer-Tropsch. We'll come on to that in a few minutes. And in terms of our traction to date, we have a plant near Oxford in the UK, in Bicester, plant 0.1. That's producing engineering quantities of fuel. We're currently closing a funding round for our next scale plant, our first commercial scale plant, plant 0.2, which will most likely be in the US. But we already have a global pipeline of plants across the world. So we're exploring a potential plant in Abu Dhabi, in Australia, in Japan, across Europe. And really, our interest in India is to potentially look at a project in India, given the great renewable energy available and the engineering talent that's available here. And yeah, last thing on our background. So in terms of partnerships, as I said, we have a partnership with ADNOC to explore a potential plant in Abu Dhabi. We're also technical partners with Rolls-Royce and Boeing, who are looking at our fuel and helping us to achieve ASTM certification for our jet fuel. We have a strong partnership with the UK Royal Air Force, who are our main sort of financial backer to date, as well as Babcock and Intertek, the fuel testing partner. So yeah, onto the topic at hand. So just kind of address the problem first. So what problem are we trying to, in fact, all of us trying to solve today? As you can see, in terms of the transport sector is the majority of oil demand in the world today. But if you break that down into its various kind of components, as you can see, almost half of all transport oil demand is in the passenger vehicle sector, which potentially could be electrified fully. Although, having said that, there's pushback around the world now, even in, say, the UK, where strict targets just around charging infrastructure and rare earth metal shortage, etc. But crucially, the aviation shipping sectors, as well as road freight sectors, are very difficult to electrify, and as I'm sure we'll come on to, it's difficult to sort of use solutions like green hydrogen, for example, due to the storage and transportation issues. And so, we believe that liquid fuels are here to stay, which is something I mentioned in the beginning, and primarily it's to do with energy density. And so, the chairs alluded to this point earlier. If you look, in terms of the energy density of a liquid fuel, batteries are 50 times heavier on average. We're looking at lithium batteries. There's now talk about moving to sodium batteries because of shortages around lithium. Those are even heavier, and so liquid fuels deliver a huge, energy dense solution for the transportation sector. When you look at hydrogen, although hydrogen is obviously the least dense material in the cosmos, ultimately the storage of hydrogen, the tanks, the pressures required mean that the energy density of hydrogen as well is actually multiples of a liquid fuel, and primarily what we're aiming for is a synthetic liquid fuel. And so why we believe synthetic liquid fuels are the answer is, firstly, the energy density point, but also crucially, they're 100% fossil free. We'll come on to the process of how we make it, but what we're aiming to do is to take carbon from the atmosphere and hydrogen from water, using hydrogen from water to make green hydrogen. The feedstock issue is less of a concern. We use 1.5 liters of water per liter of fuel, so the water consumption is relatively low compared to, say, biofuels, where you might use hundreds of liters. As direct air capture technologies advance, carbon's very sort of abundant in the atmosphere. And in the long run, we think there's some interesting advantages as well. Energy independence is a big point. So we get a lot of interest from investors and companies in Japan who are very interested in our technology, because Japan, in decades to come, could become a synthetic fuel producer. The same applies for India, where India today is a fuel importer. Again, through these technologies, in the sort of decades to come, it could actually become a fuel producer and exporter in its own right. And then, the last point is quite important, is compared to, say, biofuels, ultimately we're building a machine that creates synthetic fuel. And so we believe there's some strong Moore's law, Wright's law effects that we can benefit from to help drive down the cost, which is ultimately the main challenge that we're facing today. So compared to other fuels, and again, the chairs sort of mentioned this, so we believe that synthetic fuels offer a lot of advantages. The energy density point, the drop-in quality, you can drop straight into existing infrastructure. When you compare to biofuels, probably the closest competitor, which is another liquid fuel, as was sort of mentioned, there's many issues around feed versus fuel, the drop-in capability, etc. and ultimately the scale is sort of the challenge there. We're not against biofuels by any means. We think it's an important solution. And I think that's one thing to mention is all of the above. All of these solutions will have their different applications in different sectors. Electrification, of course, in many sectors, hydrogen potentially, but we believe that synthetic fuels in the longer run offers the most sort of potential to scale and to actually replace fossil fuels. Again, this is something we'll see, play out in the years and decades to come. So yeah, the last few slides just on our process and the technology itself. So this is a sort of broad overview of our process. In fact, I think a lot of the people here today will have similar processes. What sets us apart slightly in Zero is we aim for a fully green process. So we use green electrons, we use green hydrogen using electrolysis. On the hydrogen side, we can also be an off-taker of green hydrogen. And as you can see, almost 95% of the energy we use is on the green hydrogen side. And so our argument in terms of green hydrogen is, we're a green hydrogen company. What we do is make hydrogen easily storable, transportable, and usable in existing infrastructure. On the carbon side, currently we're using biogenic CO2 to ensure that we're fully green. As I said, as direct air capture technology advances, we'll start taking carbon dioxide and carbon from the atmosphere. But the orange box is really our sort of core IP and where our USP is. So we use a proprietary process called direct FT, direct Fischer-Tropsch. So as many of you I'm sure will know, Fischer-Tropsch is a very old 100-year-old chemical process from Germany. And traditionally, competitors of ours in the space use a cobalt catalyst-based Fischer-Tropsch process, which produces a synthetic crude, a syncrude. This has some challenges around the output and the sort of target fuel. We have a different proprietary process called direct FT, which has a lot of sort of unique advantages and we think is much more advanced from a technical standpoint. And so what direct FT allows us to do is we can create all fuel types, so gasoline, jet, or diesel. Again, Cobalt FT generally focuses on a blend stock for jet fuel, whereas we can produce all types of fuel. It's 100% fossil-free, of course, but crucially it's 100% drop-in. As I said, we're already producing the aromatics for jet fuel. We're at 96.4 RON on gasoline already, which is forecourt grade around the world. And all of it comes down to the fact that we have a highly selective process. So we can really choose and select the sort of molecules that come out of our reactor, straight out of our reactor. So for example, in gasoline, 90+% of our output is drop-in grade gasoline at this point. For jet fuel, it's 70+% already, compared to say 30% for cobalt FT. We don't use any rare earth metals in our catalysts, so we use abundant catalysts. And crucially, the fuel that comes out of a reactor, there's no blending, cracking, any post-processing, which is again an issue you have with cobalt FT, which produces synthetic crude. And so yeah, just the last slide on us in terms of our scale up and where we're at. As I said, we are, although there's all these advantages, we are a few steps behind a lot of the other people you'll hear from today and a lot of the technologies out there. So in 2021, we had our first sort of temporary pilot plant that was to create the fuel for that Guinness World Record flight, which we did in 2021. In 2023, we opened our first plant in the UK. That's producing engineering quantities of fuel. It's a 50 kilowatt plant, but importantly, the plant does everything on site. So we produce green hydrogen on site. We have solar panels on the roof. Not all the energy is green, but a vast majority of it is. So it's a fully green process all in the building, which as far as we know is the only such building in the world today. And as I said, we're currently raising a large funding round using an investment bank in the US. That's going to be for our first commercial scale plant, which should be commissioned next year in the US. That's going to be 15 megawatts in the first phase and actually producing more commercial volumes of fuel. And really our interest in India is in that 2027 nth of a kind plants. So after the first of the kind is established, to actually move towards hundreds of megawatts and actually start ramping up commercial production. But that's all I have to say in terms of the presentation. Thank you so much for listening and for your time. I guess, yeah, I don't know if you have any time for questions.
Thank you for the presentation. I think we can take questions at the end when all the sessions are over. Thanks a lot. So can I invite Filza Shaikh for her presentation on Power to X technologies.
Good morning, everyone. First of all, thank you for being present here so early in the morning. And let me directly jump into the presentation. Yeah. So, MAN Energy Solutions is actually a group of Volkswagen. And in MAN Energy Solutions, we have 4 sectors, namely the marine, where we have the 2 and 4 stroke engines. Then we have the energy and storage. In industries, we have the rotating equipment like compressors. And then we have the after sales team or the prime serve team. However, you don't see Dagendorf or TWE on this. We are also part of the Energy Solutions and actually the core hub for the Power to X technologies. So at DWE, we are actually manufacturing and designing chemical reactors, which are predominantly in the chemical industry, but we also produce components for the petrochemical sector and physical research facilities. Yeah. So, what are the technologies that are helping us to rely on our decarbonization goals or achieving our net zero? We have identified these 5 pillars as our growth paths and which are helping us to decarbonize the world. Namely, so our sister company, HTech, is producing the PEM electrolyzers. That's one sector. And then we have the green engines, where our marine colleagues are now are having the methanol engines, or so to say with the green fuels engines. And then we have the retrofits. Why retrofits? Because we need to also upgrade the existing fleet and not new vessels would come into the picture. And then we have the carbon capture and the heat pumps. Yeah. So our goal is moving big things to zero. So we are actually engineering systems for decarbonization or for the decarbonization. Yeah. So let me quote Dr. Uwe Lauber, who's the CEO of MAN Energy Solutions. He says, the industries we serve are the crucial for world economy. Most of them are also hard to decarbonize. And this gives us the opportunity to have big impact on the global energy transition. That's the reason we get out of the bed. So, as we all know, 80 to 90% of the global freight is transported by sea, which is responsible for 3% of the global carbon dioxide emissions. 50% of this 3% comes from MAN engines. That's why we take this very seriously. Yeah, so our goal is also to decarbonize the existing fleet with renewable diesel and gasoline. So our co-presenter, Mr. Prasanna, already touched a little bit about the overview of the future fuels. So here we have a comparison of the storage volume for the same energy amount. Of course, you can see the comparison for LNG, methanol, ammonia being slightly higher, and as it's getting compressed, the hydrogen, it's requiring a larger volume. So, boosting green hydrogen production. I touched slightly about HTech, who's producing PEM electrolyzers. PEM electrolyzers can handle more volatile conditions, and HTech is now one of the top global companies in producing PEM electrolyzers. Yeah, so as many or all of the respectable companies have a crystal ball department who are kind of predicting the future, so do we. And based upon our feedback from the customers, they just analyzed and put it up here, what we can see. So it's going to be a mixture of the fuels. What do I mean by that? At the moment, methanol is gaining traction. However, by 2040, it's going to be a mixture. So methanol, ammonia, renewable fuels like single fuels or diesel will also play a role. So that's the message here. Yeah. Coming to synthetic aviation fuel, so we already have been reading a lot and coming across a lot about the aviation sector that needs to fulfill its EU decarbonization quotas by ESAF. And we believe that SAF based on methanol or via Fischer-Tropsch is going to gain the largest market share by 2030. So, We were part of the Haru-Oni project, where along with the technology licensor like JM, we gave the synthetics the skid for the methanol, and the Porsche then utilized the gasoline coming from this methanol, which came from another technology partner, into their own fleet. Yeah. So our main focus is synthetic gas or methane, so to say. So we actually have our own patented technology for this, which is actually a two-stage process to produce this, which is today operated on a water-boiled reactor. Yeah, so this is one of the demonstration unit, that is the Welte Audi e-gas plant, which went into operation in 2019. 2013, and you can see here, so you have the electrolyzer, the carbon dioxide is coming from the biogas plant, the methanation reactor came from DWE, from Degendorf, and then you have the liquefaction, and this could directly be injected into the fleet system. So this is already running for several years now, or over a decade. So just an overview of the pathway. A lot of colors here. So to make it simple for you, everything that's green is actually DWE product, and sky blue is in development. However, what I would like to highlight is the methanation, methanol synthesis, along with our technology partners. We are actually into methanol to gasoline, methanol to kerosene, and we have already a partnership with Shell for the reverse water gas shift phase, which is the prior phase to the Fischer Tropsch. And at the end, you can see the end products. Yeah, so what is our focus? Our focus is on carbon dioxide, on renewable methanol. How? Because we have already been operating over carbon dioxide to methanol catalyst for BASF in our lab in Degendorf, and over 2,500 hours. However, for several decades, we are already the approved vendors for major companies like JM, Air Liquide, and we have a lot of experience in this. That's also why since 2013, our focus has also been on developing green methanol solutions along with our partners. Yeah. So I spoke briefly about the Haru-Oni project, and what you can see on the left side, this is what we received. These were the drawings that we received, which then had to be converted into detailed engineering. A lot of development was involved. And you can see on the right-hand side, which is a skid, which is a baby methanol plant. But however, that's the beginning to the large, what's going to happen next. Yeah. So I spoke about our technology partners. What we do is with BSC, our technology partner, we have methanol skids, which are 10 and 20 megawatt green methanol skids. What is unique about it is that it doesn't need any H2 buffer tank. They have very fast ramping up times and very fast lead times. So when it comes to the methanol to gasoline, with our technology partner, CSE, we have already produced over 46,000 liters at TU Freiburg. So you can see on the right-hand side, we have a reactor which is already running and producing gasoline, and this gasoline has been tested in 2 test cars. So it doesn't need any technical alteration, and also meets the EN standards for the fuel. So this is already ready to go for the large scale. And then with our technology partners, we also have methanol to kerosene, which is actually a step process which involves from methanol to olefins and further processing into paraffinic fuels, whereby the byproducts are also diesel and gasoline. So what is our key takeaway from today's discussion is that in order to reach the global warming, we need to defossilize the global energy system. However, renewable fuels have a certain role in defossilizing the hard-to-abate sectors. Various sectors will require different renewable fuels, and there will be enormous demand in the future, so there is no silver bullet, and the technology, as you already saw, is ready, and now is the time to act. This is just an example of what we delivered for the Qatar Shell project a few years ago. These are the Shell reactors, which is GTL reactors. 6 of them came from our sites. And the feed, of course, is synthetic in this case, is syngas. However, if you just change the feed to a carbon dioxide or the organic paste, then you are directly talking about a revolution that can happen. Okay. I hope I stuck to the time. Thank you very much.
Thanks for being on time. I think we have a few minutes you have given also. Thank you. So may I call upon the next speaker, Anoop Dimri from EIL, challenges with biocoal carbon neutral fuel in steam generation.
Good morning all. I'm Anoop Dimri from Engineers India Limited. First of all, good morning to everyone. I'm Anoop Dimri from Engineers India Limited. My topic is challenges with the biocoal in steam generation plant. Let's first quickly go through the brief profile of EIL. EIL is a leading engineering consultancy EPC company. It's established in 1965 as a joint venture between Government of India and Bechtel USA. In 1967, it became a wholly owned company. It has executed more than 7,000 assignment and projects worth $200 billion. It has a significant track record of entire oil and gas value chain. Has 5 decades of experience. EIL has in-house and collaborative R&D facilities and 34 active patents in its names. The EIL has an international presence in Middle East, Africa, South America, South Asia and Central Asia. EIL employee strength is around 800. And apart from oil and gas, EIL has a focused diversifications in infrastructure, strategic crude storage, fertilizer, port, like that. Let's go map a topic on biocoal. This is simple scheme of a biorefinery where main product is ethanol. I think for last 2 days we are hearing discussing about what is ethanol, what is policies regarding blending of ethanols, like that. But my topic is now further for this. We require energy for operating of this biorefinery also. Then operating, we are making by the byproduct, so from the residue, and that residue is a byproduct, and we call it a biofuel for giving the energy to this biorefinery. And these biofuels are contents of solid fuel also. This we call as a biocoal. Apart from solid fuel, we have other fluids like syrup, cake, and gases also. What is a biocoal? Biocoal is a carbon neutral fuel, solid fuels, which can replace the fossil coal in industrial purpose. It has a byproduct of biorefinery, where main product is ethanol. It can be generated through the thermochemical or biochemical process. It has a high fixed carbon and volatile matter and low ash contents. The energy density of biocoal is very high, while moisture content is low. It's a simple end-to-end of the life cycle of this biomaterial. So actually we are executing one bamboo-based ethanol plant, which is a first kind of a project. There is no any bamboo-based ethanol plant in any of the world. So we are discussing about what a biofuel we are considering for that biorefinery and that project. The biofuel in that is biocoal, starch syrup, starch cake, just from the digester and biocoal. But main fuel is a biocoal. You see, this is a picture. This is a picture of the biocoal. It is generated from the pilot plant of the licensors. It's a very small quantity we got. We see what the challenges we face. So challenges we face with this during the configuration of combined heat and power plant, and challenges during the selection, boiler technology selections. The CHP plant is used to give the energy to the biorefinery, or the energy is required in terms of steam and power. Apart from the normal requirement, we have to also meet the requirement during upset conditions and during the turn-down conditions, or during a tip of any equipment also, with the aim of having a low capex and opex requirement and utilizing all the fuels, biofuel generated within the refinery complex itself. Based on that, the Rankine-based cogeneration plant has been selected. The configuration of CHP is that CHP consists of utility boilers, but we face the challenges when selecting a utility boiler. So that utility boiler has to be designed to consume all the complete of the biofuels generated within the refinery. And it has to be start with HSD also, because in initial phase or during a commissioning phase, then there is no biofuel, then this boiler has to start with HSD so that the commissioning process can be started. This refinery can be also, in case of tripping of any one of the utility boiler, then the refinery should also sustain, let's say in the turn-down cases. And CHP also consists of steam turbine generator. The steam turbine generator is extraction cum condensing turbine, so they have a higher cycle efficiency. Steam at all level is generated to the from the extraction of steam turbine only. And we have also a backup in case of STG trips, we can take a power from the external source also. If you see the analysis of the biocoal, biocoal consists of more solid fines. The solid fines are in range of 0.1 mm to 4 mm, and around 94% fines are less than 2 mm size. Apart from fines, it has also high oxygen content is in the range of 20 to 40%, and high volatile also. Volatile is in the range of 40 to 60%. The issue is with respect to high fines, high solid fines, and high volatile metal is that when the solid fines are high in the solid fuels, then it disperses with the winds and have a more hazardous area for the operating personnel itself. Since volatile metal is also high in this biocoal, so it can catch fires also. When it comes to for the combustion, the fine coal elutes easily from the furnace, so have a lower efficiency, and the unburned carbon will be high in this case. So how to mitigate with this the properties of that high fines and this in the biocoals is simple solution is let the pelletize the fuels. If you see, if you go to pelletization, fuel size will be in this size, and this is a typical pelletizing machines. From that, we can make the fuel pelletize and make a. But we face the challenges in pelletizations also, because it is a first kind of project. We don't have any experience for this biocoal, and the amount of a biocoal we get from the pilot plant is also a very small quantity, so that is also not sufficient for the testing for this pelletization. So we have many unknown factors, like what should be the binding agent for these pelletizations, what is the handling facilities required, what is the cost of that. And with the pelletization also, we cannot totally eliminate the exposure with the air. And when we pelletize the fuel, pelletize is nothing but pressing the fuel against the dies. So it can get exposed to the high temperature, and since the volatile metal is high in the pellet coal, so the risk of catching fire itself when we pelletize the fuel. The pelletized fuel also have very high capex and opex requirement, because the number of pelleting machines may be required in terms of 6 to 7 machines, and so it requires very capital intensive machines also. Apart from capital expenditure, operating expenses will also get increased, because it requires electricity consumption of auxiliary power, as well as the dies also require frequent replacements. Apart from capex and opex, space requirement will also get increased if we go for the pelletizations. So it may have an impact on IRR. So what's to do with if not able to pelletize these machines is, then let's, instead of pelletize, let's convey the biocoal itself in a closed pipes and to the inert gas, because it has a very high volatile metals and get exposure if unsupercharged. And select the suitable boiler technology that can be suitable to consume this fuel in itself as receive its services. Apart from this, the fines, the biocoal also have high alkali content and lignin-rich content also. The issue with lignin is that if the alkali content is high in the biocoal, it have a chances to get falling of the in the pressure parts, especially in the superheater sections, and formation of sticky alkali silicate metal also during the combustion itself. With this, it can also agglomerate in the bad materials and make a clinker. If you say this is a typical, let's say, falling in the superheater sections, but when the alkali content is high, the falling may reach up to this level also. The issue with the lignin when we do lignin during the combustion is that when lignin is high in biocoal during combustion, it is tendency to make a sticky as bad materials and in a superheater also. So the possibility is high for the slagging and the clinker formation. So how to then mitigate with this the issues with respect to boiler biocoal compositions? Then we have to select a suitable boiler technology and suitable steam pressure to mitigate issues, suitable steam temperature, the flue gas velocity during the combustions, the furnace temperature, combustion technology is to be selected to mitigate these issues. So when selecting the correct boiler technologies, then we face a hurdle regarding physical property, chemical property, what we discussed earlier. And since this is a first of kind projects, we don't have any past experience or past OEM experience also don't have to consume this type of biofuels. And the quantity is also very less of the biocoal to take a pilot testing for the combustion. What are the available boiler technologies for consume this boiler? First is the polarized coal boiler. Basically, this type of boiler is used on almost all thermal coal-based thermal power plants. But when we use for the biocoal, this is to be then this biocoal has to be further crushed or powdered, less than 200 microns, and this polarized fuel then has to burn in a burner. This is a schematic diagram of how it has to be make a powder in a mill and then burn through the burners. But in this type of technology, the temperature in the furnace and the flame will be higher. Other type of technology is that CFBC boiler. This is a typical presentation of a CFBC boiler. In a CFBC boiler, solid particles burn in a bed of hot particles maintained in a flowing air. The adequately high air speeds in a bed act as a fluid and resulting in a rapid mixing of the particles. Considering the fuel properties like lignin, too much fines, alkalis, this technology is not suitable for this type of fuel. What next then? Then next is a traveling gate boiler. This is a typical picture of the traveling gate type of boilers. In a traveling gate, a coal is fed at one end of the moving chain gate. As the gate moves across the length of the furnace, the coal burns and before dropping off as. This is, you can say, the typical the feeding of a coal in a traveling gate boiler. But this type of fuel, like biofuel, the best technology is that water-cooled vibrating gate is just suitable for that. And this is a typical moving vibrating grate with the water cool. The gate is included in evaporator. Gate is included in evaporator circuit also to cool that bed also. Other is a AFBC boiler. This is a systematic diagram of AFBC boiler. AFBC technology is more suitable for this type of fuel. All the fuels, which are biocoal also and other like stainless syrup and stainless cake also, in as basis also and as a pellet form also. And in ABC boiler, we can effectively retain a biocoal, stainless syrup, stainless cake also within a combustion zone and with the low velocity also. Low velocity is required so that the fines of a coal particle cannot eludate the furnace from the furnace. The fluidization as a low velocity also promotes a complete fuel combustion at relatively low temperature. And since the temperature is low, bed temperature is low, then chances of clogging or is also very less, and we can able to maintain a low NEPS and eliminated clinker and make the boiler reliability enhancement can be also increased. So based on the technical parameters what we discussed earlier and the capex and opex requirement, the ABC boiler is selected for this type of fuels. And with this ABC boiler, the furnace design has taken further considerations also taken. We have considered a bigger furnace size so that to have more resistance times. The superheater gap between superheater is high so that the fouling can be restricted, and they have a multi-pass design system has been adopted for that. Fuel conveying also we have discussed earlier. We convey the fuel in a closed pipes for the safety reason also. And the thermal designs, we have considered that the flue gas velocity is to be kept low, but bed temperature is also be to kept low so that the clinker formation can be avoided. And frequent bed material draining is to be considered so that the chances of clogging in the bed or making a clinker is to be avoided. Thank you. Thank you.
Thank you. May I call upon Ramesh Kanaparthi, Chief Manager HPCL, to talk about photocatalytic reduction of CO2.
Good morning, everyone. First of all, I would like to thank IEW for giving this wonderful opportunity to present our efforts in this area. The title of my presentation is Solar Fuels, and I will just define what are the solar fuels. Solar fuels is something like converting CO2 and water in the presence of light. It sounds very similar, well known. It is very much similar to photosynthesis, where the natural light, in the presence of natural light, CO2 is getting converted into the hydrocarbons. So I will just, in this presentation, I will just take you through our effort. And conversion of CO2, if you see, and we are working on a lot of areas which includes CO2 to methanol, CO2 to olefins, CO2 to carbonates, and CO2 to OME, oxymethylene ether, and as well as DME, dimethyl ether. Today I am going to talk about CO2 conversion to the fuels. Fuels in the sense that I am mainly going to talk about production of methanol alcohols, that those are methanol and ethanol. These are excellent platform chemicals which can be converted into fuels and other chemicals. So I will just briefly introduce you this, the Time Magazine Top 20 Green Ideas, and where you will see 20 green ideas. In that I have highlighted, and 4 of them are somehow related to the solar energy, utilization of solar energy. That the artificial photosynthesis is also included into this. So if the main challenge of CO2 conversion is the energy required for activation of CO2. The bond energy of carbon and oxygen is about 765 kilojoules per mole. This is much higher, almost double to compared to carbon, hydrogen, or carbon bond energies. So there is a lot of energy input is required, and we have to look for the other alternative where we can convert this more easily than thermocatalytic or thermo routes. So using the solar energy, which is perennial, this is the best option. I would think that this technology is going to play a major role in the future. You can see that our HPGRDC efforts in, although we are a hydrocarbon industry and we deal with the hydrocarbon production and marketing, and we have this, serious efforts in the areas of solar and allied areas, and we have published 8 papers, plenty of conference papers, and we have also filed 13 patents. We got 17 patents granted for, our efforts in the solar area. Why we have to look into solar is basically this is a perennial, and if you see the numbers, the annual global energy usage is 4.6 quintillion joules. This is almost same energy we receive on the earth in 1 hour time. So If we can substitute this or partially this, we can save 13,000 million tons of oil equivalents. That's a huge number. So solar energy scenario in India, it is very rapidly evolving, and the total energy, solar energy capacity now it reached 72 gigawatts, and now it is one of the major renewable energy contribution, and the solar tariffs also has gone down last 10 years very significantly. And what is going to happen in the future is, they using the solar energy in the industries where we can use for chemicals production. So that is going to play a major role. We seriously believe that. And converting the CO2 to CO2 and water to the fuels is the topic today. And first step is CO2 capture. There are a lot of technologies available: adsorption membranes, cryogenic separations, then activation of CO2 and water, then to produce some of the molecules like methanol, and then convert into the fuels. Otherwise, we converting directly by photocatalytic or photoelectrocatalytic directly to produce the fuels. So this is the idea. But now still this work is still in the academic stage, or there is a significant progress which I have personally observed for last 3-4 years. I will share with you, and our efforts also I will share with you. So these are some of the routes for CO2. The main challenge is here. This is the electromagnetic, the contributions of visible light here. So 5% only UV light, and majority is a visible light. Here the challenge is how to use the visible light in the conversion of CO2 and water. That is a major challenge here. And basically what we have to do is we have to develop catalysts that work in visible range. So we can I am just showing you the concepts of photosynthesis as well as photocatalysis. But it is very similar, where this is being done by bio route, and this is a purely chemical route. And otherwise, in both cases, this is electrons get excited, and they reduce the CO2 and also oxidize the water. This is the same thing happens chemically also. And basically you have to find a suitable catalyst which has suitable band energy and band gap. That is the most important. So the design of the catalyst is going to play major role in getting the higher conversions as well as controlling the selectivity. That is the most important. So these are the functionalities required for the catalyst. The catalyst should be able to split the water to produce hydrogen ions, and the reductive conversion of CO2 to hydrocarbons. The both steps should happen simultaneously. So the most critical part in this, the idea is to design a catalyst with a suitable band energy and band gap engineering. And sometimes the original catalyst will not have a suitable band gap, which can be used in visible light. But then you have to modify the catalyst, and then we have to make that is suitable for using the visible light. So otherwise, this is the concept where UV or visible light is absorbed by the photocatalyst, and then from valence bond, then electrons are produced, and this is in conduction band, and this is used for CO2 conversion into the carbon species. So from there, based on the catalyst, and the selectivity will depend on. So all kind of CO2 reductive compounds like CO, methane, and methanol, ethanol, formaldehyde, all these are possible in theoretically, but controlling the selectivity is the most important thing. And this is the criteria of the essential criteria of the catalyst. In view of time, I will not go through all these things. And basically, it says that you have to design a catalyst keeping all these factors in the mind. And here, one of the catalysts which we have taken is a perovskite type of catalyst. This is a AbO3 structure where you will have one large metal ion and one small metal ion. And mostly these are like titanates, tantalates, diobates, and this kind of ironate, ferrite type of compounds. And we have used this sodium tantalate, and which we have modified with the lanthanum, and we formed this lanthanum sodium tantalate. And basically, we are seeing here, when you dope lanthanum, slightly band gap, increase to 4.1, and it will have an effect in the production of selective production of the hydrocarbons. And once we make this lanthanum sodium tantalate, then we have doped with, we modified this catalyst with using nitrogen and iron, and also using, we have added further magnesium oxide, basically to increase the absorption of CO2. And I will just show you the results, what we have got. Otherwise, this is the characterization, and the doping of iron and nitrogen is very uniform and homogeneous. And another effect happened is in the UVDRS spectra, where we can see that the peak maxima shifted to visible range that indicates that this catalyst can be active in the visible range. So the crystallite size slightly decreased, and the band gap is significantly decreased from 3.9 to 2.6. That is the important effect. And here we have depicted the idea of addition of nitrogen and iron co-doping, and on this particular perovskite. And we can see that on the right hand side, the results where we are producing methanol and ethanol, and there is a small amounts of acetic acid also we have produced, and mainly methanol we are producing. Suppose if you have a neat catalyst, we are producing about 300 together ethanol and methanol micromoles per gram. But if you, for the doped catalyst, final iron and nitrogen co-doped catalyst, we have significantly increased this to 900 micromoles per gram. This is very significant. In the table, I have shown all the compounds which we could able to detect. And although these are, very low levels, but this is the work actually gives, good direction. And fundamentally, this methanol we are producing about 62 micromoles per gram using the photo reduction. Sure, sir. So some of the challenges we have identified, and we have listed here. And then when we add magnesium oxide, basically our concept is we can improve the CO2 absorption, where we could able to further improve the methanol production here. So that is almost like 15%, 20% we have increased. The photocatalytic reduction of CO2, these are the improvements which are further required, and still the conversions are low, the kinetics are very slow. And there is a lot of scope for the catalyst design and application. And one of the way to deal with this one is the electrocatalytic reduction of CO2 and water. Although there are a lot of challenges to design the anodes, suitable anodes, but there is a significant work is currently going on in this area. And this is our photocatalytic reactor which we have designed in our lab, and these are the conditions we have. And the light source is mainly we are using visible light, that is a 450 watt, and catalyst amount we are taking 100 milligrams, and DMF triethyl methane and triethyl methane, and water, the ratio is 60 to 20. Reaction duration typically 5 hours we keep. And I want to show you our latest work here. The first 5 rows are our result, where we are producing methanol as well as ethanol. These are very significant results, for the one-dimensional zinc oxide modified catalyst. And this is order of magnitude higher than the earlier result, and but we are not the best so far. And there are some results which are reported on MYF type of catalysts or MILs, and which is showing even better. But those results need to be verified, and we are still aiming for the best. And we are getting about 2%, 2.5% of CO2 conversion. And another idea is to make this process continuous, where we can continuously produce, the alcohols from CO2 directly using a, photon energy. So these are the other aspects we have to evaluate cost savings and economic benefits. Thank you so much for patient listening to me.
Thank you, Ramesh, for this photo catalytic. May I call upon Dr. Sudhanshu Shekhar, sorry, from ONGC.
Good morning to one all. I'm going to present my title Development and Demonstration of Microwave Process for the Enhancement of Coal Bed Methane under Subsurface Condition. So, what ONGC Energy Centre was set up by ONGC in August 2005, and with the objective to harness science and technology to meet national energy need of tomorrow in clean and sustainable manner. What we do, we undertake, assist and collaborate research projects with various organizations. Even apart from this, we are also taking in-house project. We have our in-house facility at Dehradun. So this is ONGC Energy Centre at a glance. We are working in hydrogen generation, biotechnology, uranium and helium, solar and other, geothermal and kinetic hydro. And geothermal, very recently we are in Ladakh region, we are in the process of drilling wells for generation of hydrogen, generation of energy. And hydrogen, a pilot plant has been set up next to the hall number 3 for demonstration. This is our institute with whom we are collaborating and taking projects. This is our in-house research facility at KDMIP Dehradun, where we are taking in-house R&D projects with some assets and all. So coming to the CBM, coal bed methane is an unconventional source of natural sources and considered as an alternative source of India energy. And India is the 5th largest proven coal reserves in the world, and also holds significant prospect for exploration production of CBM. There are the distribution of coal is in the 12th state of India. And there are several companies in India in the eastern side who are working in this generation of methane. Coal bed methane is the source of natural gas produced either biologically or thermogenically. So this is the distribution of coal blocks in India, and right hand side of the screen it is CBM extraction process from the wells. CBM characterization, it is porosity. The porosity of the coal reservoir is usually very small and ranging from 0.1 to 10%. Fracture permeability, the fracture permeability act as the major challenger for gas flow. And there are some other property characteristics also, coal density, initial gas concentration, critical gas saturation and all. So potential CBM production is in early stage, several fold increase expect when all the blocks start in production in tandem. It is the clean energy, hence it can increase the carbon credit. There are benefits also, development of demonstration gas-based industry, generation of revenue from state and central government, development of new infrastructure in project and consumption center. Water produced from CBM wells can be utilized in irrigation and various purposes. So bio-CBM, a biogenic process of CBM, is the result of microbial mechanism and degradation of coal with subsequent flow among multiple microbial processes. Rising natural gas demand over the year 2000. There are several companies who are working in this field, and in this present study we have developed 2 processes, biostimulation and bioaugmentation, where what we do, this is the entire process. Here 3 processes are taking simultaneously. One acetoclastic methanogenesis process and hydrogenotropic methanogenesis and methylotropic methanogenesis process acts from conversion of coal to methane. This is the what we are doing. We are selecting the well and we are collecting the samples, and some analysis, laboratory analysis are being carried out there in the lab, and based on the laboratory outcome we are going to the field. So This is the laboratory analysis result. We optimize the media and we accordingly we implement in the field. So this is the entire process. First we collect the coal, we enrich the media, and this is the entire process till execution of work in the well. This is one of the case study what we have executed in 2016, and significant increase in the gas production has been observed when compared to the pre-job and post-job. Once the pre-job the data was 500 something, and once after execution of work job it has increased to the 2 to 3 fold. And again this is the second case study what we have taken other well. Here also increase in the gas production from 2 to 3 fold has been observed. This is also third case study where we augment the bacteria, where there is no bacterial indication were there. We culture the bacteria in the laboratory condition. We inject the media and we study the conversion of methane. This is the microbial communities from post and pre and post job analysis. And conclusion that we have executed 2 jobs. This is case study of 2 jobs, where in one valve we have got the result of 2 to 4 fold increase, and second also 3 to 4 fold increase in the production was observed. This is the research facility what we are creating while execution of job. This is gas pressure control valve skid. This is water skid for measurement of gas and water while dewatering. A joint patent has been granted in collaboration with TERI recently last month for this process. There are some challenges also in this CVM. So there are LEQ issues, policies issues, regulatory challenges is also there, lack of technical expertise and expertise in CVM related projects. There are no data available, and hence poor quality of reservoir in the terms of CVM saturation. Thank you.
We are done with all the presentation. If the audience, is there any questions to the presenter, please raise your hand and state your name, and I'm going to ask the question to the specific presenter.